Let's work through these together and also do some other problems as we review for exam 2. Actually, let's skip the true false for the moment. Let's go ahead and just jump to number 3. What is that first series that you see in number 3A? It's got a name. Harmonic series. And what did I tell you about the harmonic series? It diverges, and that's just something you are allowed to quote. We know the harmonic series diverges. You're also allowed, by the way, to quote when P series converge or diverge. A P series is a series of this form. You may use this as knowledge anytime you need it. This converges if P is bigger than 1 and diverges if P is less than or equal to 1. If I asked you to prove that, I'm not in any of these problems here, but if I did on your test, you'd want to prove it with the integral test. You'd want to consider the improper integral from 1 to infinity of 1 over x to the p and see that this converges as an improper integral if p is bigger than 1 and diverges if p is less than or equal to 1. And because the form of the terms there matches the form of the function we're integrating there, if you know this fact, that's enough to imply this fact. Doing that for a general P is probably too tricky for an exam, but maybe I'd pick a specific P, like 1/2 or 3 or 7 even, or something like that. And I'd say apply the integral test. That's not the way these problems are stated, though. Anyway, coming back to 3A, the harmonic series is a P series with P equal to 1. That is the divergence case. So this is an example of a series that diverges in spite of the fact that the terms go to 0. What does that imply about one of the answers to either number 1 or number 2? Okay, I'll say it's the answer to number 1. What is the fact that A is the harmonic series and diverges imply the answer is to number 1? Go ahead. False. Yeah, 1 is false. And the harmonic series provides an example where it's false. Because the harmonic series, the ANs are 1 over n. They go to 0. The terms, the sequence of terms converges to 0. But the series, the infinite sum, does not converge. It diverges. Always want to make sure you get the distinction between them, between the terms and the series. Any series, any infinite sum actually has 2 sequences associated with it. The sequence of terms that are being added, the ANs, and also the sequence of partial sums. S1 was A1, S2 was A1 plus A2, S3 was A1 plus A2 plus A3, etc. Those A's and S's are related. And the only way the SNs are going to have a chance of converging is if the ANs go to 0. But just because the ANs go to 0 doesn't mean the SNs converge. The partial sums of the harmonic series as a sequence diverges. And that is what it means to say the harmonic series itself diverges. Right? That's the definition of what it means for a series to converge or diverge. You got to look at the sequence of partial sums. What's the answer to B? Converge or diverge, the series. Go ahead. It diverges, and what's the reason? The terms don't go to 0. That's called the divergence test. And unless your series happens to be, say, obviously geometric or something, it's really the first thing you should think about. I said that a few weeks ago. The divergence test, unless your series happens to be obviously geometric or some other obviously recognized form, is the first thing you should check. Those terms that are being added there, they are getting small. Just saying they're getting small, though, is not enough. They got to go to 0. They're getting small. They're getting closer and closer to 1 over 1,000. 0.001. Close to 0, but not equal to 0. And because the terms don't go to 0 exactly, that's enough to say this series diverges. That's the divergence test. If the terms don't go to 0, the series diverges. I claim that's relevant for figuring out the answer to number 2. Is 2 true or false? Somebody else? Go ahead. 2 is true. It is essentially the divergence test, or you might say it's the contrapositive of the divergence test. The divergence test, in its easiest to use form, is if the ands do not go to 0, then the series whose terms are the ands diverges. This is the contrapositive of that. If the series whose terms are the ands converges, then the ands must go to 0. Switching around the P and the Q and negating them both. 2 really is the divergence test. At least it's contrapositive. An implication, an if-then statement, and it's contrapositive mean the exact same thing. And if one's true, the other's true. And if one's false, the other's false. C. Converge or diverge? And what did you use? If that n in the numerator were a constant, it would be a geometric series. But it's not a constant. Both the top and the bottom are getting large as n gets larger. However, intuitively, well, this is not a proof, 2 to the n is growing big faster, much faster than n is, making this fraction go to 0 pretty rapidly. For example, when n is 10, it's 10 over 1,024, close to 0.01. If n is 20, it's 20 over 2 to the 20th. 2 to the 20th is a bit over 1,000,000. 20 divided by something a bit over 1,000,000 is much smaller yet. These terms are going to 0 pretty rapidly, but pretty rapidly is a very vague statement. But we would guess convergence. How would you prove it? The ratio test, yes, is the best thing to use. N over 2 to the n are the terms. These are the ANs. For the ratio test, we have to compute the limit as n goes to infinity in the general case of the absolute value of an plus 1 divided by the absolute value of an. However, these terms are positive, so we can get rid of the absolute value signs. An plus 1 is what I get when I replace each n with n plus 1. So I'll get n plus 1 over 2 to the n plus 1. Dividing by an means multiply by its reciprocal. Multiply by 2 to the n over n. Two to the n plus 1 by a property of exponents is 2 to the n times 2. We get cancellation. So this is now the limit as n goes to infinity of n plus 1 over 2n. A rational function of n. You could evaluate this limit if you pretended n was a continuous variable by using L'Hopital's rule, or using the things I told you in the past. The degree of the top and bottom are the same, 1. So just look at the coefficients of the highest powers. This is 1/2. And what's relevant about that answer for deciding if the series either converges or diverges? Yeah, if this limit is less than 1, that means the series back here converges. This is, I'm not using the divergence test here. I'm not looking at the ANs themselves. They do go to 0. The divergence test is not relevant. This is a different test. We got a limit less than 1, therefore the series converges. If the limit had been bigger than 1, then the series would diverge. And if we had gotten a limit equal to 1, then the ratio test is not helpful. No information. It might converge, it might diverge. In fact, I think I mentioned this before, if you try to apply the ratio test to any P series, you'll get no conclusion. You'll get a limit of 1, no matter what P is. So, well, we know the P series converges if P is bigger than 1 and diverges if P is less than or equal to 1. Try the limit test, the comparison, the ratio test with a P series, you'll get a limit of 1. The ratio test is not helpful there. Best thing to do in that example is to consider the integral test. ND is got a name as well. Go ahead, Michael. Ultimating harmonic series. 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 ... I told you that series, somebody over here, it actually converges. The harmonic series itself diverges. That's this one. But the alternating harmonic series, what did I say that right? The harmonic series diverges. The alternating harmonic series converges. It does fit the conditions of the alternating series test. So you can either quote saying, we know the alternating harmonic series converges, or you can apply the alternating series test. Somebody had a question?
That would be basically what to say that.
Okay. Yeah. This test, this series does fit the pattern of alternating series where Bn is 1/n. The Bn's are not the terms. It's the -1 to the n plus 1 times the Bn's that are the terms. But if those are your terms and you identify the Bn based on that, which is always positive and decreases, technically speaking, monotonically to 0. Monotonically means it's always decreasing. It doesn't like go down, then up, then down, then up, then down, then up, and eventually still go to 0. It's always decreasing towards 0. Decreases monotonically in one direction effectively. And that's enough to satisfy the conditions of the alternating series test. And we can conclude that this series converges. I didn't really emphasize the distinction between absolute convergence and conditional convergence in class. It was in the reading. This converges conditionally, and that's kind of a weaker kind of a convergence. And one bad downside of conditional convergence is that if you rearrange the terms in a different order, you could get a different sum. That doesn't happen with absolutely convergent series. You can rearrange the terms in any way you want with absolutely convergent series. I'm not going to dwell on it. I'm not going to test you on it. Just wanted to mention it. For sake of time, we'll skip number 4. You probably should have gotten that it converged. You probably should have gotten a limit less than 1, I'm guessing. 5, it's a proof problem. the key inequalities to use in number 5 to prove what you want to prove are, first of all, that the terms are non-negative. Secondly, that e to the negative n, if n is a positive integer, is always less than or equal to 1. And thirdly, if I get rid of the 5 in the denominator there, I get yet a bigger fraction. This fraction is smaller than this one because the tops of the fractions are the same, but the bottom on this one is bigger. I'm dividing by a bigger positive number there. That's got to be smaller, closer to 0. And the series whose terms are 1 over n cubed is a p-series with p equal to 3. It'll converge. And then these inequalities plus the comparison test would allow you to say the series that we're interested in, this one, converges. If I have you do a proof with the comparison test, you need to be very careful how you say things, including in the last line, making sure you put the summation sign there. If you don't put the summation sign in appropriate spots, you're completely missing the point. It's fundamental to the proof. The alternating series test has an error bound in it. I'll let you work through this problem. Here's some problems that we haven't done a ton of examples like, but certainly A and C we have done to some degree. B is a little different. What would you say about part A? What kind of series is that? It's got a certain pattern. Certain kind of name that starts with the letter G. What kind of series do we have that starts with the letter G? Geometric. It is a geometric series. There is a common ratio that is any term divided by the previous term. Negative 2/3. Negative 6 divided by 9 is negative 2/3. 4 divided by negative 6 is negative 2/3. Negative 8/3 divided by 4 turns out to be negative 2/3. Alternatively, given any term, to get the next term, multiply by negative 2/3. So we know that as long as that common ratio has an absolute value less than 1, which it does, absolute value of negative 2/3 is positive 2/3, which is less than 1. That's enough to say the series converges, and we can even find its sum to be A over 1 minus the common ratio, which sometimes we called X and sometimes we called R. I'll call it X like we did at first. A is the first term, that's 9. Common ratio is negative 2/3. Two negatives in the bottom make a positive. 1 plus 2/3 is 5/3. 9 divided by 5/3 is 9 times 3/5. It is 27/5, which is 5.4. That's what the series in A converges to. C is also a geometric series, but it's a finite geometric series. There's no plus dot dot dots at the end here. There's in the middle there are, but here that's the last term. A finite geometric series written in this form, A plus AX plus AX squared, etc., through AX to the n minus 1. Reason we use an n minus 1 and not an n is so that our series here, our finite geometric series, has n terms, because we're starting with effectively a times x to the 0 power. The first term has x to the 0 power. The second term has x to the first power. The third term has x to the second power. The nth term has x to the n minus 1 power. And here's what it equaled, as long as x was not equal to 1. So you would apply that for part C here. A is the first term, 3 X is the common ratio, 1/2, not 3/2, 1/2. And what is n? How many terms are there in part C? 20? 21. Because the first one is really 3 divided by 2 to the 0 power. Because 2 to the 0 power is 1. So there's 21 terms. So now you'd use these numbers and plug into that formula to get the answer. B is a little different, but you should be able to handle something like B. It should at least feel a little familiar. Doesn't that seem a little familiar? Like to what we did even at the start of class today? E to the x. This looks like the series for e to the x, except there's no x's in there. Well, what have I really done? I've replaced x with 2. So in other words, this has to converge to e squared. That's the answer, e squared. Let's compute some partial sums. See how close we get. 1 plus 2 plus 2 squared over 2 factorial is 2. 2 cubed over 3 factorial is 8, 6. Which of course reduces to 4/3. 2 to the 4th over 4 factorial is 16 divided by 24, etc. I have powers of 2 in the numerator and factorials in the denominator. 5040 is 7 factorial. We are pretty close to e squared. Almost out of time. I want to give you some hints about a harder looking problem. Number 13. The globular cluster M13 is a spherical distribution of stars which orbits our galaxy. Really? Yeah. There are globular clusters. Essentially, they're mini galaxies that are shaped like spheres instead of spiral galaxies. They're shaped like spheres. They are out there. You can find them. In fact, I looked through a telescope once that was zoomed in on a globular cluster. It was on Westmont College's campus in California, where I saw that. They had to have an observatory. Suppose the density of stars in the cluster is purely a function of r, the distance of a point from the center of the cluster. Suppose the density is given by this formula, a certain number of stars per cubic light year. A light year, we talked about light on Wednesday. A light year, right, is how far, it's a distance. How far does light travel in 1 year? Which is very far, many billions and trillions of miles and kilometers. So the nearest star is 4 light years away, 4 times further. So a cubic light year is a cube with 1 light year distance on each side. How many stars are there typically in a cubic light year? I'm guessing it's typically a fairly small number, probably a decimal less than 1 in general. R goes from 0 to 100 light years. The goal is to set up a Riemann sum which approximates the total number of stars. Then write down a definite integral whose value is the exact number of stars, though take that word exact with a bit of, that's hand wavy. It's not really exact because this model is probably not perfect. And then part C, evaluate the integral. Are you kidding me? We got to integrate something involving this function. Doesn't look very easy. Take a breath. What would be the way to approach this? Draw a sphere. Pretend all the stars in the globular cluster are inside that sphere. the sphere is 100 light years in radius. For any given radius, that's an Ly, by the way, Ly, 100 Ly for light year. The assumption in this problem is for any given radius between 0 and 100, say right here, that the corresponding sphere that you could create with that radius, if it has a tiny bit of thickness at least to it, we could multiply the density of stars per cubic light year times the small volume of the thin shell of a sphere. Just talking about the outer part of it, not the inside, to get the approximate number of stars in the thin shell. Because that density is in stars per cubic light years. If you found the volume of the shell centered at the origin, multiply the density times that volume, you'll get the approximate number of stars. You could say delta S for small number of stars in this thin slice, S represents the number of stars, is approximately the density rho of R times delta V, the volume. This is stars per cubic light year. And this is in cubic light years. Those are going to cancel to give you stars. But what is the volume? I got to integrate with respect to R, right? R is the radius going from 0 to 100. I got to write the volume in terms of R, and maybe the thin thickness of this shell of a sphere, thickness delta R. Thickness delta R is what I just wrote there. Take that thickness, multiply times the surface area of the sphere, and you'll get the approximate volume of the thin shell. 4 pi r squared is the surface area of the sphere, and delta R is its approximate thickness of the thin shell. And essentially, this thing, by letting delta R go to 0, becomes the function that you integrate from 0 to 100. And it's not as hard as it might seem at first. Because of the 4 pi r squared in there, and rho involving essentially an r cubed, you'll be able to do a substitution to do the integral. In fact, W equals what's inside the parentheses will be a substitution that works. Okay. See you on Monday. Remember that we start 5 minutes early and end 5 minutes late.